This question is from section 11.3 in the book, which is inference about two means that are independent samples, so not paired, unpaired samples. This is problem number 2 from the homework. So we're not given a scenario for this problem, we're just given some summary data about our two independent samples. We have the n for each sample. We're told they're normally distributed because the requirement is that n is greater than or equal to 30 for each one, or they're normally distributed, the populations are. So we are able to perform a t-test on this, and we're going to test whether the mean from the first one is greater than the mean from the second. So we're doing a right-tailed t-test at a 0.1 level of significance. And then we're also going to construct a 90% confidence interval, and we're going to do this using StatCrunch. So first of all, with these questions, the null hypothesis is always that the means are the same. And then the alternative hypothesis is how they are different. So here, the alternative is that the first one is greater than the second, which again is given in the question. Then we're asked to determine the test statistic, so we do that in StatCrunch. Okay, so here's StatCrunch, and we're going to go ahead and do stat, t-stats, 2 samples with summary, because that's what they gave us. So the sample mean for the first one, that's our x bar, 46. Sample standard deviation is our s. Sample size is our n. Again, mean 36.1, s 7.5, and our n is 13. Okay, so we make sure this pool variances is unchecked, which it is, and then we match what we were given in the problem. We're doing a right-tailed test. So we're also asked for the critical value here, and so we're going to go ahead and ask it to display the critical value in our summary. So when we hit compute, we're given our test statistic, that's our t-stat, and we're also given our critical value here. And so one of the things I wanted to point out is another thing about the critical value. If you look in the book, the critical value is basically the same as the critical value from the smaller sample, degrees of freedom. And so you could have also, well, you could have used the table that they provided to give you the critical value, but you could also go in and go to calculators and do the t-calculator to find the critical value using the smaller degrees of freedom, which remember is just n minus 1. So I can put an n here of 12, and we're going to do greater than, and we'll do our value here. So that's our level. This is right-tailed, so our level of significance is 0.1. So I type that in there. And so I get as a critical value using this t-calculator, which matches this table, of 1.356. And notice it is slightly different than the critical value that shows up here. And either of those critical values would be marked correct in the homework. And the reason that they're different is because you could calculate the critical value in 2 different ways. You can use this smaller degrees of freedom, or they provide this really complicated formula to calculate degrees of freedom for the critical value in the textbook, which shows up if you click on View an Example. They'll show you this crazy long calculation for the degrees of freedom. And so I just wanted to point out that there is more than one way to calculate the critical value. If you had used this degrees of freedom calculation to calculate it, then you get the number that showed up in our output from this doing the hypothesis test, this critical value. Again, either one of these would be marked as correct when you're typing your answers into my lab statistics. Okay, I hope this helps.